In this course, the concept of resilient urban form topologies will be examined through selected case studies from different scales and contexts. Within the scope of the presentation, the ways in which urban morphology shapes cities' exposure, vulnerability, and adaptive capacity in the face of climate change and multiple hazards will be discussed. Key spatial components such as density, building topologies, street networks, open and green space systems, and topography will be analyzed through examples to demonstrate their impacts on heat waves, floods, inundation, earthquakes, and climate-related risks. Furthermore, it will be emphasized that resilient urban forms are not limited to physical interventions alone, but must be considered together with ecological integration, accessibility, emergency response mechanisms, and multi-layered planning strategies. In this context, the course aims to enable students to comparatively analyze different urban form topologies and to understand the role of spatial decisions in achieving long-term urban resilience. The following case studies are examined to illustrate the role of urban form and planning strategies in enhancing resilience: Hammarby-Sjöstad, Stockholm, Medellin Green Corridors, Colombia, Tokyo Firebreak Districts, Japan, and the Copenhagen Cloudburst Plan, Denmark. By the end of this section, students will be able to analyze how different urban morphology topologies influence cities' exposure and resilience to multiple hazards such as heatwaves, floods, landslides, earthquakes, and urban fires. Students will also be able to explain the role of blue-green infrastructure, open space networks, and street morphology as spatial risk mitigation mechanisms in different urban contexts. In addition, students will be able to evaluate how integrated planning approaches combine environmental performance, disaster risk reduction, and everyday urban life, and apply insights from the case studies to support risk-sensitive and resilient urban design and planning decisions. Hammarby-Sjöstad, located close to the city center of Stockholm, represents a landmark example of an ecologically driven urban regeneration project where sustainable development principles are implemented through an integrated morphological strategy. The district was developed by transforming former industrial and brownfield areas into a compact, mixed-use, and environmentally responsive urban form. Its spatial structure demonstrates how urban morphology can actively contribute to risk reduction and climate adaptation. Building orientation, block configuration, and street layouts are designed to enhance ventilation corridors, reduce urban heat island effects, and support microclimatic comfort. At the same time, blue-green infrastructure systems, including canals, wetlands, green corridors, and open space networks, are embedded into the urban fabric to manage stormwater, mitigate flooding, and strengthen ecological connectivity. Energy, water, and waste systems are integrated into a closed-loop model, reinforcing both environmental performance and resilience. As a result, Hammarby-Sjöstad stands out as a strong case study illustrating how sustainable urban form and multi-hazard risk reduction can be addressed simultaneously through morphology-based planning. This aerial image showcases Hammarby-Sjöstad, a sustainable urban development example with a compact yet low-density urban plan. Key features include optimal spaces between buildings that allow for sufficient natural light and air circulation, wide pedestrian corridors ensuring smooth movement and social interaction, blue-green infrastructure integrated into the design, combining water systems, canals, and green corridors for environmental benefit. Hammarby-Sjöstad's design directly contributes to mitigating the urban heat island (UHI) effect, maintaining airflow, and naturally managing stormwater. The incorporation of green areas and water management systems serves to reduce surface temperatures and enhance ecological connectivity across the district. These morphological elements not only improve environmental quality but also bolster the resilience of the city in the face of climatic challenges, demonstrating a holistic approach to urban planning and climate adaptation. Street geometry and climate adaptation through green infrastructure. This street-level view of Hammarby-Sjöstad illustrates how urban street geometry is deliberately designed as a climate adaptation tool. The narrowing of vehicle lanes, combined with wide pedestrian and bicycle paths, prioritizes non-motorized mobility while reducing traffic-related heat and emissions. Green buffer zones, rain gardens, and permeable surfaces are integrated along the street sections, enabling stormwater to be collected, filtered, and gradually infiltrated into the blue-green infrastructure network rather than being rapidly drained through conventional systems. Tree-lined streets and vegetated edges provide shading and evapotranspiration, which significantly lowers surface and ambient temperatures during warm periods and mitigates urban heat stress. The pedestrian-oriented design not only enhances thermal comfort but also supports social interaction and everyday usability of public space. Through these spatial strategies, street sections function simultaneously as mobility corridors, microclimate regulators, and ecological systems, demonstrating how climate-responsive street design can strengthen urban resilience while improving environmental quality and livability. This visual presents the historical evolution of urban morphology, the transformation of planning practices over time, and the spatial logic underlying the diverse urban fabrics observed in contemporary cities within a comprehensive analytical framework. It enables the city to be read not merely as a physical built environment, but as a multi-layered spatial system shaped by social, economic, technological, and environmental dynamics. The diagrams on the left side illustrate the main morphological phases of European cities throughout history. Medieval urban fabrics are characterized by organic and irregular street patterns, narrow and winding roads, and compact building blocks, reflecting defense-oriented layouts, pedestrian-scale movement, and limited transportation technologies. With the Industrial Revolution, urban form became more regular yet remained dense and block-based, driven by industrial production, population growth, and proximity between housing and workplaces. In the early 20th century, the influence of garden city principles introduced more dispersed, green-oriented, and low-density residential patterns. During the suburbanization phase, parcel sizes increased, road networks expanded, and residential areas became more homogeneously distributed. These typological representations clearly demonstrate how dominant social, economic, and technological conditions of each period reshaped urban form. The central section of the visual focuses on urban fabrics produced by modernist planning approaches, characterized by rational, ordered, and functionally segregated spatial structures. In this panel, transportation infrastructure, particularly metro lines, arterial roads, and ring corridors, emerges as a primary driver of urban development. New urban centers are designed in direct relation to transit networks, while peripheral residential areas are organized through regular block patterns, hierarchical open space systems, and zoned land uses. The spatial separation of residential, commercial, and industrial areas highlights the increasing role of functional zoning as a defining principle of modern urban morphology. This section emphasizes how modernist planning transformed cities into more predictable, geometric, and infrastructure-oriented systems. The large, color-coded map on the right demonstrates how the typological frameworks presented in the previous panels manifest within an actual urban geography. Residential districts of varying character, commercial centers, industrial clusters, green space networks, and water systems are represented in an integrated manner, allowing the functional and ecological structure of the city to be analyzed holistically. The spatial diversity extending from the historic core to newly developed areas becomes legible through land use patterns, transportation corridors, and blue-green infrastructure networks. When read as a whole, the visual illustrates that urban morphology is both a historically evolving process and a structurally guided system shaped by planning policies and infrastructural decisions. The left panel reflects inherited spatial logics, the central panel highlights modern planning paradigms, and the right panel reveals how these layers coexist within contemporary urban organization. This integrated perspective underscores that morphological topologies are not merely abstract theoretical constructs, but operative frameworks that interact with mobility systems, ecological networks, and functional zoning in real urban contexts. This diagram illustrates Hammarby-Sjostad's integrated urban metabolism model, which demonstrates how spatial planning, infrastructure systems, and environmental management operate as a closed-loop system. The district is designed to link energy, water, and waste flows in a circular manner, transforming traditional linear urban systems into a resilient and resource-efficient network. Wastewater is treated and reused, solid waste contributes to energy production, and district heating and cooling systems are supported by renewable and recovered energy sources. This integrated approach shows that urban resilience is not achieved solely through physical form, but through the synchronization of morphological decisions with environmental infrastructure. The compact yet permeable urban structure supports efficient service distribution, while blue-green infrastructure enhances stormwater management and microclimatic regulation. By embedding ecological cycles directly into the urban fabric, Hammarby-Sjöstad exemplifies how sustainable urban form can simultaneously reduce environmental impacts, enhance climate adaptation capacity, and improve long-term urban resilience. Medellin is located in a narrow valley surrounded by steep slopes, resulting in an urban morphology that is strongly shaped by topography. The concentration of settlements on hillsides increases exposure to landslides, erosion, and rainfall-related risks. In response, the city has developed a resilience-oriented urban form that integrates green corridors, topography-adaptive mobility systems, and slope stabilization strategies. Through the Green Corridors Program, 2016 to 2019, urban streets, riverbanks, hillside paths, and public transport axes were connected via 18 linear ecological spines, forming a continuous environmental network across the city. These corridors aim to reduce urban heat stress, manage stormwater more effectively, and enhance soil stability on slopes. By aligning urban development with natural landform constraints rather than overriding them, Medellin demonstrates how topography-responsive planning can transform environmental vulnerability into a structural component of urban resilience and climate adaptation. This aerial view further illustrates how Medellin's dense informal settlements adapt directly to steep valley topography. The compact building pattern follows contour lines, minimizing excavation while increasing exposure to landslide, erosion, and drainage-related risks. In response, recent resilience strategies focus on strengthening slope stability, improving accessibility, and integrating green corridors and linear infrastructures into the existing urban fabric. Rather than replacing the morphology, Medellin's approach works with topography, transforming risk-prone areas into structurally and environmentally supported urban systems. The Medellin Green Corridors Master Plan represents a city-scale resilience strategy that integrates urban morphology, topography, and climate adaptation into a continuous ecological system. The plan is structured around 18 linear green corridors that connect streets, riverbanks, hillsides, and public transport axes, forming an ecological backbone across the city. These corridors function as urban wind corridors, strengthening north-south and east-west airflow, dispersing accumulated heat in dense urban canyons, and reducing urban heat island intensity. At the valley scale, the strategy directly responds to Medellin's steep topography and climate-related risks. Dense vegetation on slopes stabilizes soil, reduces erosion, and slows surface runoff during intense rainfall events, lowering landslide and flood risks. Along the Medellin River, blue-green infrastructure transforms flood-prone edges into ecological buffer zones that manage stormwater while enhancing biodiversity and public space quality. Overall, the Green Corridors Master Plan demonstrates how topography-driven, linear ecological systems can simultaneously improve thermal comfort, manage hydrometeorological risks, and strengthen urban resilience in compact, high-density cities. This slide presents the measurable impacts of the Medellin Green Corridors Master Plan in addressing climatic and geomorphological risks. Through the implementation of nature-based solutions, an average 2 to 3 degrees Celsius reduction in the urban heat island effect has been achieved across the city, with particularly significant decreases in surface temperatures observed in asphalt-dominated neighborhoods. Permeable surfaces, biofiltration swales, and rain gardens retain rainfall during storm events, reducing the risk of flash flooding and alleviating pressure on the conventional drainage and sewer systems. In hillside areas, the combined use of vegetation, surface water management, and drainage systems has lowered runoff velocities, thereby reducing the likelihood of reaching landslide-triggering thresholds. This integrated approach demonstrates that ecological infrastructure in Medellin functions not only as an environmental enhancement, but also as a strategic urban tool for disaster risk reduction and climate adaptation. The Tokyo case demonstrates how open space morphology was strategically reconfigured to address earthquake and fire risks within an extremely dense urban fabric. Following the 1923 Kanto earthquake, Large-scale parks and wide boulevards were deliberately planned as firebreak corridors to prevent the rapid spread of post-earthquake fires. In areas characterized by narrow streets and dense wooden housing, the urban fabric was restructured through the introduction of linear open spaces that fragmented high-risk zones and improved emergency access. These open areas also functioned as evacuation and assembly spaces, providing safe gathering points during disasters. Importantly, the system was conceived as a connected open space network, linking parks, corridors, and public spaces into a continuous morphological structure rather than isolated elements. This planning approach marked a turning point in Tokyo's urban reconstruction, establishing open space not only as a social amenity but as a critical component of disaster-resilient urban form. As another case, the Copenhagen Cloudburst Management Plan demonstrates how urban morphology can be strategically reconfigured as a flood-adaptive spatial system in response to increasing pluvial flood risks. Rather than treating stormwater management as a purely technical infrastructure issue, the plan reframes the urban fabric itself as an active component of water governance. In this approach, streets are no longer conceived solely as transportation corridors. Instead, they are designed as controlled morphological flow paths capable of safely conveying excess runoff during extreme rainfall events. To achieve this, street sections are selectively reprofiled, with adjusted road levels, carefully designed curbs and sidewalks, and calibrated surface gradients that direct water movement. While these spaces operate as conventional public realms under normal conditions, they temporarily assume the role of blue corridors during cloudburst events. This layered functionality exemplifies a robust form of morphological adaptation, in which everyday urban life and flood-resilient infrastructure are integrated within a single spatial framework. Copenhagen Cloudburst Management Plan demonstrates how urban morphology can be strategically redesigned to manage extreme rainfall events. Rather than treating flooding as a purely technical problem, the plan integrates streets, parks, and open spaces into a connected water management system. Street sections are reshaped to guide excess rainwater safely through the city, while low-lying parks and green corridors function as temporary retention and storage areas during cloudburst events. Permeable surfaces, biofiltration elements, and controlled surface gradients increase infiltration and delay runoff. Under normal conditions, these spaces operate as everyday public realms. During heavy rainfall, they transform into functional flood infrastructure. This approach highlights a holistic, morphology-based adaptation strategy where urban form actively contributes to climate resilience. Copenhagen Cloudburst Management Plan represents a resilient urban design approach developed to address flash floods caused by intense rainfall events. Instead of relying solely on underground drainage infrastructure, the plan restructures urban morphology to manage water on the surface. Streets, parks, and open spaces are redesigned to function as controlled flow paths and temporary retention areas during extreme rain events. Under normal conditions, these spaces operate as everyday public realms. During cloudbursts, they safely convey and store excess stormwater. This integrated system distributes water loads across the urban fabric, reduces pressure on drainage networks, and minimizes flood damage. The Copenhagen case demonstrates how urban form itself can act as a climate-adaptive infrastructure, enhancing resilience without compromising daily urban life. Copenhagen Cloudburst Management Plan demonstrates how urban morphology can actively function as a flood-responsive system under extreme rainfall conditions. In this approach, street sections are reconfigured to guide stormwater along predefined flood routes rather than resisting it. Variations in street width, elevation differences, curb design, and surface materials are carefully calibrated to control water flow direction and speed. During normal conditions, these streets operate as everyday public spaces. During cloudburst events, they temporarily transform into safe water corridors. Permeable surfaces, low-lying green areas, and blue-green infrastructure elements are integrated to slow, store, and redirect excess water. This model illustrates how urban form itself can become a proactive risk reduction tool, enhancing resilience while maintaining daily urban functionality. This example illustrates how rainwater management is integrated with urban space design within the Copenhagen Cloudburst Management Plan. Street sections and public spaces are reconfigured to guide and temporarily store stormwater during extreme rainfall events. Under normal conditions, these areas function as everyday public spaces, while during cloudburst events they transform into safe water corridors, demonstrating how urban morphology can operate as an effective risk reduction tool. By combining blue-green infrastructure with adaptive street design, the plan enhances urban resilience while preserving the usability and quality of public space. As illustrated in the table, each case addresses a distinct hazard context by mobilizing urban morphology as a key resilience mechanism. Hammarby-Sjöstad integrates compact urban form with blue-green infrastructure to reduce heat stress and manage flooding. Medellin employs topography-adaptive green corridors to mitigate landslide risk and improve microclimatic conditions. Tokyo utilizes open-space firebreak morphology to control post-earthquake fire spread, while Copenhagen restructures streets and parks as flow-directing systems to manage cloudburst-induced flooding. Collectively, these cases demonstrate the critical role of urban form in hazard mitigation and adaptive urban resilience. This presentation highlights how urban morphology plays a critical role in shaping cities' exposure and resilience to multiple hazards, including heatwaves, flooding, landslides, and post-earthquake fires. The case studies demonstrate that spatial strategies such as blue-green infrastructure, topography-adaptive corridors, firebreak open spaces, and flow-directing street networks function as effective risk mitigation mechanisms. Overall, the examples emphasize that strategic spatial planning significantly enhances urban adaptive capacity in the context of escalating climate and disaster risks.